y1 ex cosine x and y2 ex sine x are solutions of the differential equation y double prime minus 2y prime plus 2y equals 0. So showing this is a solution means simply plug in this function. I mean, this is y, plug in here and get 0. Okay, so y prime, y double prime. So we need to plug in y prime and y double prime. Here is y. That means we need to find y prime, first derivative, and second derivative. Okay, so let's do it. So here y, this y1, we are just saying y, same thing, or y1 is y, e to the x cosine x. Okay, so let's find derivative y prime. So we got a product of two functions. That means we must use the product rule. So derivative of ex is ex cosine x plus derivative of cosine x is negative sine x times e to the x. And we also need y double prime. So let's find derivative one more time. Now we got a product here and another product. So the product rule twice. So here ex is ex times cosine x plus derivative of cosine is negative sine x times ex. Okay, these two terms coming from the first product plus, okay, I'm just saying this plus, okay, here derivative of negative sine, negative cosine x. I mean, negative is negative and derivative of sine is cosine times ex plus, now find derivative of ex, which is ex itself, negative sine x. Then if we look at closely, ex cosine x, which is plus, ex cosine is minus, so we can cancel these two terms. Okay, that leaves negative sine x ex, same thing, negative sine x ex, so negative 2 copies of ex sine x. Okay, now plug these into the ODE, which is y double prime. Y double prime is here, negative 2 e raised to x sine x minus 2y prime minus 2y prime. So y prime is here, so we need to distribute negative 2. So negative 2 times first term, okay, negative 2 times second term. So negative, and we are distributing negative 2. Okay, here negative 2. That negative make this positive sine x e to the x and 2. Okay, plus 2y, plus 2 times y, plus 2 e to the x cosine x. And we are trying to see if this is equal to 0. Let's look at the right hand side. 2 sine x ex, 2 sine x ex, these two cancel, and 2 cosine x ex, 2 cosine x ex, they also cancel. That means we got 0 equals, I was asking if this is true. Yes, all that means this y1 is a solution. Okay, that means y1 e to the x cosine x is a solution of the ODE. Similarly, we need to show e to the x sine x is also a solution. So pretty much it will be exact same work. Okay, let me make it slightly smaller. writing. So let's do the same thing. So here we let y, that's y2 as y, e to the x sine x. We need to find first derivative, again using the product rule. Derivative of ex is ex sine x plus derivative of sine is cosine x. I got ex cosine x. Let's find second derivative. So here is one product rule plus here is another product rule. Using the product rule, ex is ex sine x plus derivative of sine is cosine, so e to the x cosine x plus here e to the x is e to the x cosine x plus derivative of cosine x is negative sine x. I could have written ex here or ex here, doesn't matter. And if we look at closely, ex minus ex sine x is a plus ex sine x, so these two cancel and we can combine the middle two, ex cosine x plus ex cosine x. In fact, two copies of ex cosine x. Now we want to plug these into the ODE, which is y double prime, that's 2 e to the x cosine x minus 2y prime. So minus 2, we need to distribute minus 2 here, minus 2 ex sine x, and here minus 2 ex cosine x plus 2y plus 2y, y is ex sine x, and we are checking if this is 0. And 2ex cosine x, these two cancel and these two cancel as well, they are same, this plus minus, that means yes, 0. Okay, this implies y2 e to the x sine x is a solution of the ODE, y double prime minus 2y prime plus 2y equals 0, or just the ODE. And the question also wants us to show a linear combination of these two solutions. By the way, we show individually they are solutions of this ODE. Now the question is asking their linear combination, where C1 and C2 are arbitrary constants, is also a solution. So what I'm going to do is, we need to show, let me write, I need to show C1 e to the x cosine x plus C2 e to the x sine x is a solution of the ODE. Okay, the ODE, the differential equation I wrote here. So we want to show this one, but we already labeled the name ex cosine x. We can, that's the solution we saw here. We call that y1. So I'm going to write this as, okay, this is y1 essentially, this is y2, so that our work becomes neat. Okay, so here we are trying to show y equals this is a solution. Okay, and I'm writing in shorthand notation y1. So c1 y1 plus c2 y2, where y1 is a solution, y2 is also a solution. Okay, this is y. Now we need to find y prime. Now it will be the same like previous two cases. Okay, find y prime, and here c1 is a constant, so y1 prime plus c2 is constant y2 prime. We can go back and write down the values of y1 prime. I mean, this is y1 prime here, and this one is in fact y1 double prime, right? Because this is y1, and if we come here, this is y2 prime, and this is y2 double prime, by the way. Okay, so we can use that, and y double prime will be, then just find derivative one more time. C1 is constant, survives, y1 double prime plus C2 y2 double prime. Okay, now plug these into the ODE. So y double prime is here now. C1 y1 double prime plus C2 y2 double prime minus 2y prime. That's the ODE. Look at here, 2y prime. So y prime is here, so we need to distribute -2. -2 C1 y1 double prime minus 2 times C2, my bad, it's not double, just okay, y2 prime, that's the second term, plus 2y, 2 times this, so distribute 2, 2c1 y1 plus 2c2 y2. We are trying to see if this is 0, I'm asking. Okay, now we need to plug in the values of y1 double prime, y2 double prime. Okay, that's the case, but we can separate into two parts, having y1 prime, y1 double prime, y1 prime, and y1 in one place, and the others y2 in other place. Okay, so here what I'm trying to do is C1 C1 C1. Look at these y1 terms, so I can factor C1 out. That leaves y1 double prime minus 2 C1 is out, y1 prime plus 2 y1 plus from the terms containing y2 we can factor C2 out, so y2 double prime minus here 2 y2 prime plus 2 y2. We are trying to see if this is 0, so this is C1, so y1 double prime, let's do this work. So when we plug in y1, I mean this one is y1 prime, y2 prime, I mean that was this. Okay, -2 ex sine x minus 2 ex cosine x plus this one, so essentially 0. Okay, when we had y1 e to the x cosine x, y1 we found first derivative here and second derivative. Then when we plug that into differential equation, I mean that's the case, y1 double prime minus 2 y1 prime plus 2 y1, that is pretty much the differential equation. Okay, so when we do this we get 0. I mean you can plug in those values, y1 double prime, up, and this one -2 e to the x sine x minus 2y1 prime here plus 2y1, so you're going to get 0, plus C2, same thing, you're going to get 0. Now we are asking if this is 0. Yes, C1 times 0 is 0 plus C2 times 0 is 0, so yes, this is 0. So what does that mean? That means C1 y1, which is ex cosine x, plus C2 y2, which is ex sine x. This one is also a solution of the ODE. Okay, so here's one lesson, by the way. When we have a homogeneous differential equation, any y double prime plus any number y prime, it could be a function as well, plus by equals 0, where a, b could be functions, okay, or constants. And if we have one solution y1 and y2 another solution, then any linear combination c1 y1 plus c2 y2, that is also a solution. Okay, and this solution is called the general solution. And essentially we proved this one here. We showed y1 a solution, y2 also a solution, then we showed c1 first solution plus c2 second solution is also a solution. Okay, final.